Okay, good. The recording started, so we can look at the website. Next link is model calibration and validation. I changed the order yesterday, so be patient. We are advancing step by step. And later on, I will also make an exercise on what we did last time and what we are doing today. So let me just check if I have a PowerPoint. I don't think so. So if not, I use the Blackboard. Yeah, I don't have a PowerPoint here. Very good. I keep the screen there because I want to keep a reference for you and for me. But let me work on the Blackboard, and therefore I need to, just give me 1 second, I need to change the camera. Okay, good. Let's see. Perfect. And let me try to put it in evidence. And let me, can you check in Teams? When I put, because I put in evidence the camera and the Blackboard, do you see the Blackboard big or small? Small? Okay, so let me share the screen then. Now you should see the Blackboard. It's big now. It's big. Okay, good. Okay, so last time we talked about models, and we talked about the rational formula and the linear reservoir. These are just 2 examples of mathematical models used to predict Earth system processes. These are just a couple of examples which are related to rain-for-runoff modeling. As we know, we are using rain-for-runoff modeling for its relevance in climate change adaptation, and as an example of how a mathematical model can be used to predict, to simulate what's happening into nature. And I may use several other examples. Another example may be, for instance, a water quality model, given that today we spoke about water quality. There are mathematical models describing what happens into a body of water, maybe a lake, maybe the sea, maybe a river, when pollutants are released, when a sewer system releases with or without depuration some contaminants. There are mathematical models describing what happens in terms of indicators of water quality. This is another example. Other examples may be models that predict the evolution of glaciers. With an increase of temperature, they try to predict what's going on in the ice caps and the distribution of glaciers in mountains regions. This is another model that allows us to predict the change in the future that we may expect in several Earth system processes when temperature increases, when climate changes. So the examples may be several. And I said that there are also climate models which are trying to predict what will happen to climate with increasing emissions of CO2. So I made 2 very simple examples. And very simple examples, let's say, the first one is very simple. The second one is a little bit more elaborated. By the way, look at the mathematical development of the linear reservoir, which has been amended by me on my slides. And please try to understand it, because it may also be a question at the exam, how to derive the expression of the linear reservoir under constant rainfall, which is something that you can fully derive analytically. Okay, so there are several examples that we can make. There is one common feature in all models, which is the use of parameters. This is one of the common features of the feature that they share. So the use of parameters. What are the parameters? We define them as features, as coefficients in the mathematical relationships, which can assume a value that is constant or varying in time. And what is the purpose of these coefficients? To adapt the model to a specific context. So the model doesn't change in its structure, in its physical principle, in its functioning. It is the same model that is adapted to a different context. For instance, I use the rational formula for the Po River or for the Danube River. It's the same formula, but I expect that the area of the catchment changes, that rainfall changes, but changes also the coefficient C, which is a parameter. Okay, it's a parameter. It's called a parameter because while the area of the catchment reflects a physical attribute, while rainfall is a physical attribute, the coefficient C is okay, reflects the losses, so it may have a physical meaning, but it cannot be directly estimated. It cannot be. It is something that we need to change to adapt the model to the situation. You may say also rainfall has to be changed, but rainfall I can derive it with observations. I don't have any way of estimating the parameters based on physical reasoning. Some researchers try to give a physical attitude to parameter, a physical meaning, but this physical meaning is something that is never so direct like rainfall. Physically, I understand what is the area of the catchment as a clear physical meaning. The losses, the coefficient C, water losses, it's an example, can be related to some features of the catchment, but in a very indirect way. So this is the definition of a parameter. It's a coefficient. We call it a coefficient because the physical meaning is not something directly clear. You understand that if I call the area of the catchment a coefficient, this wouldn't be appropriate. The area of the catchment is the area of the catchment. But when I talk about in the rational formula, let me write it again because I want to, well, in the rational formula, I write C, which is runoff coefficient is called, as I said, runoff coefficient. Times E rainfall times A area. You understand that these two have a clear physical meaning. They are physical entities. This one, okay, can be associated to water losses, so it has some physical connection, but it is something that it's not so clear physically, and therefore we call it coefficient or parameter. And if I change C, the model doesn't change in its structure. I'm not adding complexity. It allows me to adapt the rational formula to different rivers, to different contexts. And let me give another example. In the linear reservoir, I said that I started from two equations. I said dWt in time, dWt, the t is equal to qt minus, I hope I used these symbols, qt minus pt. So Q is the outflow, clear physical meaning. P is rainfall, clear physical meaning. Wt is storage, clear physical meaning. And then I used another equation, which is Wt is equal to K Qt. Okay, so clear physical meaning. What about K? K is a coefficient. It says the dimension of a time. If you make a dimensional analysis here, it's a time. So some authors have proved and it is mentioned this in my web pages, have proved that K is close to the time of concentration of the catchment. So K has a physical meaning. Time of concentration, we defined it. Has a physical meaning. On the other hand, it's close, but it's not really the time of concentration. And therefore, we call it a parameter. K is a parameter. It's a parameter with some physical meaning, but it's a parameter. And thus, the question is, how can I estimate this parameter C? How can I estimate K? What is the best value? Okay, the physical connection can help me. So I am expecting that K, as a dimension of a time, is close to the time of concentration in the catchment, but it's not the same thing. So I have to find the best value for K. Good. Parameters can be found in any model. Actually, there are some models, very specific situations, which are called non-parametric because they don't have parameters. So you may also hear this term, a non-parametric model, which means no parameters. There are pros and cons. It avoids a problem because estimation of parameters is a problem. On the other hand, a non-parametric model usually is less flexible. So, yeah, please.
Will we be required in this course to estimate parameters or questions by ourselves?
Yes, we will develop. We will have an exercise next hour with parameter estimation because this is indeed a problem. Okay. So, for instance, if you think of a model to predict the time taken by a body to reach the soil, the parameter may be gravity, but gravity indeed is, because otherwise it's the only parameter, because we know that the time taken by a body to reach the soil only depends on gravity. The gravity can be considered a parameter in some cases, but actually, usually we know the value. So this is an example of a model which doesn't require calibration. We may call it non-parametric. Doesn't require parameter estimation. Sorry, I used a term that I still have to introduce. I used calibration. You don't know what it means. So let's use parameter estimation, which means that the model, in a way, may be called non-parametric. It doesn't need really parameter estimation, this model, which I mentioned. But typically, Earth system models, they include parameters because there are several approximations in these models, several simplifications, there is uncertainty. And therefore, to use a flexible model allows us to reduce this uncertainty. But we are faced with a problem, the problem of parameter estimation. And this is a problem that is often mentioned in climate change. Parameter estimation is often mentioned because climate models themselves, they rely on parameters. For the definition that I gave of a parameter, sometimes it's not really easy to recognize immediately into a model structure what is a parameter and what is not. Like I made the example of gravity. Gravity is not a parameter, it's a physical quantity, which we know. On the other hand, if you make assumptions in the model that I'm using to describe the time taken by a body to reach the ground, there is a fundamental assumption, usually, which is the fact that I neglect the resistance of air. I assume that the body falls into the void. But actually, in some cases, the resistance of air is important. So if I drop my phone, and is better not, but if I drop it, it has the cover, but still, if I drop the phone or I drop a sheet of paper, the time taken by the two bodies is different to reach the ground, while the physical theory says that they should take the same time. What is the problem? It's the fact that they follow into the air, so limited resistance for the phone, the sheet of paper goes down with a lot of resistance from the air, and therefore, in this case, gravity may be also considered like a parameter. I tune gravity to compensate for the assumption that I made. But still, I hope that you understand what is the difference, at least the concept of this difference. But I also want to tell you that when you see a model structure, it's not immediately clear what is a parameter and what is not. And another thing, the parameter I said can be constant or varying in time. Just also keep in mind this, varying in time or varying in space. Gravity is varying in space, for instance. We know that gravity is not the same everywhere. There are changes in gravity over the Earth's surface. Okay, so we have this problem. We have to estimate the parameters, and this process is called with several synonyms. It's called the parameter estimation. It's called optimization, model optimization. It's called model calibration, very widely used. Calibration, you understand what it means. Adaptation, it means I adapt the model to something, I estimate the parameter. So calibration, optimization, parameter estimation, parameterization, model parameterization, they mean the same thing. So how can we estimate parameters? This is the subject of our discussion today. And in ancient times, not very ancient, like 40 years ago, they didn't have computing means, just maybe hand calculators for computing the 4 basic operations or computational powers, but they didn't have computational facilities. So the reality was much different. And therefore, they used a procedure which is called trial and error. Trial and error. I think that the name speaks for itself. For instance, for calibrating the linear reservoir, they started with a trial value of K. And then they run the model and look at the results. And the results very often at the first attempt are very bad. So you look at the results, you gain an interpretation of what's going on, why the model is bad, and then you make another iteration. They change the value of K, increased or decreased, based on the interpretation of the results. Typically, they use a graphical visualization. They looked at an hydrograph, observed and simulated. So, for instance, if they had an observed hydrograph like this, and this is observed, they tried with the first value of K, and then they got something like this. This is simulated. So, by looking at this result, I may have an interesting question for you. Right, you get something like this. Okay? From the linear reservoir. This is the linear reservoir. Linear reservoir with trial K. So the interesting question for you, we may make a pool, is if you look at a result like this, K should be increased or decreased? I don't want the answer now, but I don't give you the answer now. And this is something that you may use as a test to check if you understood what we are talking about. And if you understand a model by looking at the result in this way, a model with a single parameter like the linear reservoir, you may understand if K needs to be increased or decreased. And this is a question I'm not expecting the answer now, because you have to think of it. If I got an answer now, my thinking of it would be this was just a guess. And the student was right because it was a guess. Just, of course, you have 50% probabilities to be correct. So I don't think you should have the answer already, but just think of it. And then they said, okay, on the basis of the first result, they said, okay, this is wrong. I should increase or decrease, but they had clear. They had clear because the modeler, once that the modeler applies a model, the modeler has to get clear the interpretation of the result. They must be able to elaborate an interpretation, and they were able to elaborate an interpretation. Like you, when you will apply the model, you will be able to elaborate an interpretation basing on the trial. And then they changed, and they got something like this one. And then they said, okay, the change was too much, so let's try in between. And maybe that in between they were able to find a simulation that was satisfactory. This is trial and error. The trial and error procedure has an advantage. The advantage is that you really understand what you're doing. Otherwise, you are not successful with the trial and error procedure. You really understand if K should be increased or decreased. You understand what happens if K is overestimated. You understand what happens if K is underestimated. You get the concept. And then your uncertainty as an engineer decreases. When you understand what you're doing, your uncertainty is immediately mitigated. This was a big advantage of the trial and error procedure. The disadvantage of this procedure was that it was very long, and the disadvantage was that when you use a model that is very complex, it's not easy to understand what's going on. So imagine that you have to calibrate not just one parameter, but 100. Climate models may have hundreds of parameters. How this is possible with the trial and error? Because you need to try so many combinations. One parameter is increased, the second is decreased, the third is kept constant, the fourth is increased, the fifth is increased for several hundreds. It's impossible. I mean, manually, it's impossible. Already with 5 parameters, when I tried sometimes, I used rainfall models have a number of parameters typically that varies from 1 to 15, 20. And I tried with several models at 5 parameters. I tried with 5 parameters. It's really time taking. You have to work a lot. And you need every time to draw a graph because otherwise you cannot get an interpretation of the results. And this is for all the models. This consideration is for all the models. If you just look at the numbers, the simulation may be 1,000 numbers. The hydrograph may be 1,000 numbers. You don't understand. You need to use a visualization to make a synthesis to emphasize the concept. Okay, so you understand why at the beginning they elaborated very simple models like in the rational formula. The linear reservoir is still simple. They needed simplicity also for this reason, for model calibration, for parameterization or optimization. They needed simplicity. But then, fortunately or unfortunately, it depends on the point of view, the computational facilities came, and therefore, on the one hand, the availability of computational facilities allowed researchers to test more complicated models. more complex models. And from complexity, you also expect more fidelity, of course. And on the other hand, they had a second problem, which was to find a way to optimize the models by using the computational facilities, by using advanced techniques which allowed them to manage several parameters. And the idea was, why not to use an automatic procedure, something that can be done directly by the PC without our control, a model calibration that can be done with the PC without our control. The idea was to emulate the trial and error procedure, but to make it automatic. So the idea was to use the computational facilities to make the assessment of the performances. So to substitute our intervention in the visualization of the performances and in the assessment of performances. The idea was, let's try to make it automatic, because the computer is very fast. I can perform several trials, several combinations, but what I need is an automatic evaluation of each trial by the PC. So I'm not, they were not more concerned by making 1 million of trials, because provided that they don't need to evaluate each trial personally with human intervention. So each trial must be evaluated directly by the computer. How to do that? The idea was to substitute the visualization with a numerical quantification of the performances. So let me gain some room on the blackboard. So the idea was to introduce a numerical evaluation of performance. So we need a number that provides a performance assessment. We need a quantitative evaluation, so a number that provides a performance assessment. So what could be this number? There is a first trivial idea, which is to compute for each data, each observation that is simulated, to compute the difference between the simulation and the observation. So let's suppose that you have a vector of observations x. Okay, so x it's a vector which is equal to x1, x2, x3. So let's limit it to 3. Okay, and then this is let's say, let me remove the, okay, it's fine. And now we have a vector x hat, which is given by x hat 1, x hat 2, x hat 3, etc. And the vector can contain 1 million numbers. There is no limit. When you have a computational resource like we have now, it's not a problem. You know that in R you can handle vectors with millions of numbers. And then I can compute the difference between the two. So epsilon is a vector which is equal to x1 minus x hat 1, x2 minus x hat 2, x3 minus x hat 3. We can compute this vector of errors, let's call them, okay? And what we want is that these errors small as possible. I want to get the smallest errors, but I have many of them. So how can I find, given that I have several errors, at the end of the story, I need a number. As I said, I need a number quantifying the performances. So how can I find a synthesis of this error, a summary of these errors? So the first very simple idea is to compute something like, let me just look at the symbol that I used on the website. I want to use the same symbol. I hope that I used X. Yeah, I used X. Okay, but it is, I use time, but it's okay. Okay, FT. Okay, let me just, first idea was compute a quantity F, which depends on the parameters. Let me call theta the parameter vector. The parameters may be more than one. So in general, let's indicate with theta the parameter vector of my model. It can be a climate model. As I said, this vector may contain 500 parameters. There is no limit. So this function, which depends on the parameter value, is given by the sum of epsilon squared. This is the vector epsilon. I square it, and I take the summation of the vector of epsilon.
Can you move back?
Back, do you mean, so back you mean, because it's not included the blackboard in the, is this okay? Okay, very good. So let me explain what I did here. I squared the errors. I squared the difference between each observation and its corresponding simulation, and I summed them. So this objective, this function, this number is called sum of squares, or sum of squared errors, or least squares. Why least squares? Because I want this f be the smallest possible. Of course, f depends on the parameters, because the hats, the simulation, depends on the parameters. So if I change the vector theta of the parameters, I change then the vector x hat, and therefore I change the sum of squares. This was an idea. And you may ask me, why the squares? Because I don't want negative and positive errors to compensate. This is a very trivial answer. I take the squares because I don't want errors with different sign to compensate each other. This is a first explanation. Actually, there is a more complicated explanation, because there are also statistical reasons for taking the squares. Because you may say, if I want to avoid compensation, I could take also the absolute value of the errors. I don't need to square. On the other hand, you understand that the results change. So if you take the absolute values instead of the squares, you get different parameter values, different optimal parameter values. So there is also a statistical explanation. They elaborate the statistical explanation, which we are not interested in. It's enough for me to mention it, which suggested to take the squares. Let's just, for now, be happy with this answer. of course, I need to avoid compensation, and they used at the beginning, this is the most used way to quantify the performance of a model. Least squares is the most used. And they came to it to avoid compensation between error with different sign, but also through a statistical assessment of the results. This is important. An assessment of the results is important because what we are doing now, it's important that you get this, is to substitute a human intervention with an automatic assessment, an automatic evaluation, like if when I make the exams to you, I substituted my subjective human evaluation with an automatic performance. Would you be happy or not? I'm not sure you would be happy. If I was you, I wouldn't be happy. Because it's clear that the human intervention, the human assessment, the human evaluation is subjective. On the other hand, you understand that it's more reassuring if you trust the teacher, if you trust the person who evaluates this performance, you feel reassured with respect to an automatic assessment. If you trust the teacher, and in general, I mean, a machine, if everywhere was decided by a machine, would you be happy? If you take a plane and the plane is guided by a machine, would you be happy? It may happen in the future, but now you would say, I prefer a pilot, even if the pilot is a human, can make mistakes. But so it is extremely important that we assess the results. Because once we substitute the human intervention with the machine in whatever, we need to make tests, make sure that the machine is, so it is important that at the end they test and then choose the least squares. Because, what we are doing is a big step. And as an engineer, once that you trust a PC, you are making a big step because, you're responsible for what you decide. And then you don't want to take the risk of going to jail because the machine made a mistake. You want to test it. So what I'm saying is when we use these automatic procedures, let's try to be very careful to understand what a model does. And when you get the final results, just make an assessment, a visual assessment, make your assessment like, okay, this result is fine. It's good, I trust it. Don't blindly use a PC. Okay, let me just show you. I share the screen just 1 second. And okay, let me share it. So least squares, there is a link on my website. Let's see if it works. Yes. You see there is a Wikipedia page, and it is a bit complicated because it involves these statistical considerations that I made, and we don't need them. I just wanted to show you that if you Google for least squares, and you get a lot of entries because this is an important technique. Okay, least squares. You see how many. In Italian is metodo dei minimi quadrati, how many entries you get. Okay, this is a first example of what we call, just 1 second, I go back to what we call objective function. It is a function because it's a numerical assessment, a function of parameters, okay? And here you see that it's written in a different way with respect to on the blackboard is simplified, but you see the difference between simulation and observation. Here on the screen, it's expressed as a function of time, which is fine, but maybe also a function of space, different. The important thing is that there must be a correspondence, observation and the corresponding simulation. And then you take the difference, u square, and you take the sum of the squares. This is a first example of an objective function. So when I make calibration by minimizing the subjective function. In this case, it's a minimization. You can call it optimization of the objective function. And what we do is an automatic calibration. And then you should have a question at this stage. How can the computer change the parameters? How can the computer make a subsequent trial? Because with the trial and error procedure, I said, look at the blue hydrograph and decide if K has to be increased or decreased. So how the computer can take this decision, the decision that I asked you to take, how the computer can take it. Okay, this is a relevant question, especially because you may have 500 parameters. So how can the computer decide? If I cannot decide, how can the computer decide? Okay, there is a first possibility, which is a random generation of trials. The parameters are randomly generated. And each time you evaluate the objective function. With the PC, you can make millions of trials. So this is a random search. At the end of the story, you perform like 100 million trials, and you keep the parameter values that gave the best result. This is a possibility. Millions of trials. Several trials, random. Okay, and another possibility is that the computer performs a guided search. Why? Because millions of trials can take a lot of computational time. So they had this problem about 30 years ago. They had the PC available, and then they started with this random search, but they realized that the computer was taking weeks to perform these millions of trials. This was a problem. And then there was an intensive research activity that started beginning of the 90s of the past century, and lasted for about 15 years on how to perform a guided search. We don't need details. We just need to know now that any of the softwares that we use to make computation, Excel, MATLAB, R, as routines that are embedded, which are widely tested, which perform these millions of trials and find the optimal solution with the least squares. We don't need details. We just need to know that they are several. If you look at MATLAB or R, you have several routines to make this guided search. They differ for performances, but we don't need to go into the details. We only need to know how to use them and to look at the final result, to check if everything is matching our expectation. You understand that there is uncertainty in this procedure. So I say, look at the final result. There is uncertainty. Even if you perform millions of trials, it's not guaranteed that you get to the best solution. So there is uncertainty, which is the reason why people try to analyze the result statistically. Statistically, because they had several trials, millions of trials, and they wanted to understand what was the performance of this objective function. And they tried different forms of it, because you can take also the fourth power. you can raise the power. And again, I don't want to go into the details, but I provided some links so that you know that there are terms like consistency, unbiasedness, which apply to estimates or to objective functions. So when you may hear somebody saying least squares is consistent only for Gaussian data. So I want that you don't feel like you get lost with these terms. So I'm mentioning them, but we don't need to go into the details. And it's just enough for you that you know the terms. And then if in your future you will have the need for learning these terms, if you know them, it's very easy to learn them. If you don't know something at all, then it becomes a problem. So this is why I'm mentioning consistency and unbiasedness once again, because you may hear somebody saying least square is biased with non-Gaussian data. And if you don't understand anything, and it's a problem. Bias, you understand what is bias, but understand what it means. What it means a biased estimator. It's a little bit more difficult. We don't need to learn this now. So at the exam, I will not ask you what is consistency and biasness, but I provided the link just because I think it's important to know the terms. Okay, and to close our discussion on the least squares, this is also called a quadratic estimator. You know why? Because it's raised to the power of 2. Quadratic estimator. It's not the only one, and let me introduce the next one, and then we make the break. There is another quadratic estimator which is widely used in Earth system modeling, which is equivalent to least squares, is just a different way of presenting the results. Why they felt like the least square was not very clear, why they felt that they needed to present the results in a different way. Because with least squares, you get a number which is usually very huge. Like the sum of squares is 3 millions. How to understand if 3 millions is good or not? Even if it's the minimum, I perform like several millions trials. It's the minimum, it's 3 millions. It's good or not? So it is not transparent. When we came to discussing climate change, we realized that we need to be transparent when presenting the results. You cannot go to people and say, the model works well because the sum of squares is 3 millions. They don't understand if the model is good or not. So we need transparency, and therefore we realized that it would be better to give the results, to express the model performances with a number varying in the range of, for instance, 0, 1. So 1 means the model is perfect. The perfect model. Sum of squares is 0, okay. Perfect model, sum of squares is 0. But the model is never perfect, so 3 millions is good or not? Instead, if I say the perfect model is 1, and my model is performance 0.9, 0.9 is 90% of 1, good, it's okay. But if the perfect model with least square is 0, and I get 3 millions, I don't understand what is the comparison. Instead, if I have an objective function that gives 1 to the perfect model and decreasing numbers for decreasing performances, I can compare to 1. It's much better. So they wanted to express the result of sum of squares in the range 0, 1. And the idea was to write the objective function in this way. I think it's better if I project it over the screen. It is equivalent to the least squares. What you see at the right-hand side in the fraction at the numerator, there is least squares. There is sum of squares. So look at the right-hand side. Fraction, the numerator, is sum of squares. Now, look at the denominator. It's sum of squares, but the prediction is given by the average of the observations. Over bar X is, in this case, indicating average. So I assume that predictions are substituted by the average of the observations. Let's stop here for now and let's take a coffee. Take a coffee.
I'm also interested in doing it. Do I send you
Yeah.
an email? Or?
So, yeah, send me an email. Let's discuss privately, okay?
Okay.
Because now we need to. Okay, sorry, I apologize. I was late also coming back from the break. I have some commitments, academic commitments, which kept me busy. So I apologize once again. I got a question which is related to the schedule of our lecture, which I think is interesting for everybody. Just 1 second, I open the calendar of the lectures in May. 1 second. So if you see the calendar of the lectures, you see that in May, there are no lectures online. So this is a good question. The student who noted that. You see that in May, the last lecture online is May 25, but we have a break between April 20 and May 25. The reason is that we have a number of lectures allowed to be delivered online only, which is limited. And it was scheduled at the beginning of the calendar by the university. So I'm not allowed to exceed that number. So this is why in May you see only 3 hours per week. Now, my plan is I cannot exceed the number of online lectures. So this is the number given. But my plan is in May to look for a room where I could deliver the Thursday lectures in hybrid mode. Do you understand what I mean? Like, I cannot give them online only, but I could keep 5 hours per week in hybrid mode. The problem is the room, because on Thursday I don't have a room. So I'm looking for a room in May in order to give also on May 11 and May 18 lectures on Thursday, but this is to be confirmed. So I cannot change the calendar now. These lectures on Thursday will be in hybrid mode. So who is attending online only doesn't have any difference. Okay, there is the difference because when I am online only and don't use the Blackboard, so it's easier for students who are attending online to attend online only lectures. But I think it would be an opportunity for anticipating the end of the course. So I hope to finish my lectures actually not on May 25, but on May 18, okay, something like that. Is it this clear to you? Okay, but I need to confirm because I need a room. I think in May the room will be available, but I cannot ask the room now because if I ask now, they say no, the room is not available. But I think that some of my colleagues will terminate their lectures and I'll be able to find a room, and then I will discuss with you, of course. But for sure, I cannot exceed the number of hours online only. I hope it's clear. Okay, good. Let's go back to this. As I said, the kind of rescaling of least squares. So look at the right-hand side, the ratio. At the numerator, you have least squares. At the denominator, you have least squares where predictions, simulations are substituted by the mean of the observations. X over bar is the mean of the xt. Clear? Why this? Because the mean is, in absence of any model, is the best prediction that you can make. If you don't have any model, you have only observations, and you're asked to make a prediction. You don't have any additional information. You only have the numbers. Your best prediction is the mean, is the average. Okay, it's clear. If you have a series of numbers and you don't have any model, any additional information, what is your best prediction for the next one? You would compute the average. So the average is taken as a reference of model with minimum performances. Less than that you cannot have, or less than that it's not reasonable. So this is why least squares is divided by the least squares with respect to the mean. So this ratio that you see at the right-hand side, this fraction, is 0 for the perfect model, because you have 0 at the numerator. And it may go, if it goes to 1, it means that your model that you are optimizing, is as good as a prediction based on the average only, which means it's useless. If you have a model that performs like a prediction that you may make based on the average, is a useless model. Note, the model may perform even worse than the average. This means that the model is dangerous. It's not only useless. It's absolutely to be avoided. Is this clear? So they had the idea of comparing the performances of the model, the predictions by the model, with the prediction given, the most simple prediction that you may think of, the average. And if the model is worse than the average, it means that it's dangerous, it's to be avoided, absolutely. If the model performs like the average, it's just useless. Okay, so at the right-hand side, you see 1 minus this ratio. So what is the range that you may expect for the results? Let me now go over the blackboard. Yeah. Because you get the sum of squares at the numerator here, which is larger than the prediction based on the average, which means that your uncertainty by the model is larger than those of the average. But let me just write on the blackboard, because I want to make, and then I will show the blackboard in the camera for those who are remotely connected. Now let me write f theta. Let me use the same symbol. Is equal to 1 minus sum I equal 1 to n of xt minus x at t. Okay, squared. Squared. And then the denominator I have sum I equal 1 n of xt minus x at squared. Okay, let me just now get the blackboard big. Okay, good. First, let me define the average. This bar is equal to sum I equal 1 to n xt. Okay, this is the definition of mathematical average, and then let's see what is the range of the result that I may expect. So case perfect model. Perfect model. Perfect model. I get the sum between 1 and n of xt minus x at t squared is 0, and therefore I get f theta equal 1. So perfect model, I get a value of 1. Good. Useless model. Useless model, I get that the sum between equal 1 and n of xt minus x up p squared is equal to the sum I equal 1 to n of the denominator, so it's x p minus x average squared, and therefore I get f theta equal 0. If something is not clear, please ask. And then last case, less than useless model. Less than useless. And let me just write f e x theta lower than 0. The average, let's call it trivial prediction. Let me see if the blackboard is included. Yeah, more or less.
What's the name of this?
Correct. I didn't tell it. So this is called, this objective function is called Nash-Sutcliffe efficiency. So let me write it somewhere. I take a box here to write it, okay? It's called Nash-Sutcliffe efficiency. This is a typical question at the exam. Objective function. Can you please write down the expression for the least square objective function and the Nash efficiency? This is a typical question. Once again, this is equivalent to least squares. It's equivalent. The result is precisely the same. It is more transparent because you see that it is very easy. You are presented the performances. If it is 1, you are happy. It will be never 1. But if it is close to 1, you are happy. If it is 0, you just say, okay, the model is useless. I don't need it. If it's less than 0, it's a problem. The model is less than useless. It's to be avoided. So the Nash efficiency is in the range minus infinity 1. Minus infinity square parentheses. Minus infinity 1. Once again, the difference is not computational. If you give it, if you use it on the computer, Nash efficiency is the same as least squares. The difference is in communication. Okay. Questions? We are not yet done with the objective function, but before moving forward, I prefer to make an example of computation. So let's dedicate these remaining 25 minutes to working with R with a very simple example. As I said, I'm not done with this lecture, which is if you go to the web page, let me share the screen. Just 1 second, I make some clearing. Okay. Model calibration and validation. So there is least squares, Nash Sutcliffe efficiency. And then there are other objective functions, very simple ones. And then I need also to discuss some more about calibration in general to give you some considerations. And also I need to make a particular discussion on climate models, because climate models usually are not calibrated this way. And but anyway, I don't want to move forward now. I prefer to open now this exercise here. Just 1 second. I go back to our page exercise, trend analysis for a time series of daily river flows. And in this case, the model that I am using is not the rational formula, is not the linear reservoir, is just a trend analysis. So the model that I used is just a straight line to interpolate the data. And if you click on this, it gets a zip with a PDF, which I am opening. But just 1 second, because I want to make sure that I am sharing the screen. It was not shared. So let me just go back 1 second here. And 1 second. Okay. Here. I clicked on trend analysis for a time series of daily river flows. I got a zip. The zip is here, and I open the PDF, and the PDF is here. So trend analysis. We have a generic river at a river cross section of a river. Main daily river flows were observed, thus obtaining 20,000 values. It's a time series. Data reported in this file. Okay, we need to estimate the linear trend in the time series by minimizing the sum of the squared interpolation errors. So it's sum of squares. Let's forget about the other questions, okay? And then what I need to do is I have this file with the data. I save it in the desktop. Let me just put it over the desktop here. Okay, cannot go into the desktop. In Documenti, I put it in Documents. Good. Okay, it's in the Documents. And now I start an R window. An R console, just a console. Let me just change the font in order to, sorry, in order to increase it. So size 20. Good. And I clear the screen. So I have this console. And good. Let me put it here. 1 second. Okay, good. Okay, so let's upload the data. And to upload the data, you know, let's say river flow, you know how to do. I make a scan. Scan. And it's the file name, I don't remember. It's synthetic river flow. Okay. Okay, I uploaded the 20,000 numbers. Let's make a plot of it. Plot river flow. Type equal line. This is my river flow series. So in cubic meters per second, it's quite a big river, and it looks like there is an increasing trend. If you look at this time series, if you look at it, this is not observed. This is something that I generated, okay? So, of course, it's easier for me to say it looks like there is a trend because I know that there is a trend, but it indeed looks like there is an increase over time of the river flow. We could also check it when we get these perceptions. We could, we could check it by computing like mean river flow from 1 to 5,000. And this is 1485. And let's now compute the mean from 15,000 to 20,000. And you see that indeed it looks like the mean is increasing. When I make these computations over the screen and you don't understand something, you have to stop me, okay? Even if you don't have to feel shy or to feel like I'm not understanding because it's my fault, okay? You don't have to make this assumption. If you don't understand something, like I really got lost in what you're doing, you have to let me know, okay? I hope I am convincing. Okay, so it looks like there is a trend. Now we have to estimate it. One thing, in the web page, there is a suggested R file. Let me get it. It's here, suggested R code, and we can download it. I think it is downloaded. Oh, okay, it's here. And you see that there is the scan. Let me increase the scan. So it's the instruction that I'm using here. You can find them on the web page. Okay, perfect. Now we have to estimate a trend line. You know that the trend line has an equation which is I'm writing this on the blackboard. The trend line is my model, the model that I want to optimize, to parameterize. It's a straight line. Of course, it cannot be perfect. You know, if you look at the time series that I plotted just a few minutes ago, and you imagine of, you think of reproducing it with a straight line, of course, it's not a perfect model. It's a very simple model that we can use just to understand if there is a trend. Okay, so the trend is given by y, for instance, let's call the data y. Yt is equal to a plus b t. Okay, t here is varying. T is varying in 1/20,000. Let's forget about if they are days or if they are years. Actually, if you look at the plot, it looks like there is seasonality. So probably it's the daily river flow. It's written in the exercise, it's daily. But let's take that it's varying from 1 to 20,000. Good. And this is the trend line. What are the parameters? Theta is given by A, B. These are the two parameters. This is the intercept. And this is the slope. I am interested in particular in the slope. Okay. Unfortunately, we have two parameters, so the problem is not so easy. Okay, let's simplify it and let's take A, let's fix it. Okay, let's fix A for now, and then we will remove this assumption. A, we take it equal to 1485. So I fixed for now. Fixed for now. So I can just change the slope. Okay, so given that it's fixed, let me go over the console. A equal 1486. Fixed. Good. Now, let's now compute the trend line. So the trend line, let's use here. Y is equal to, it's equal to A plus B is not defined. So let me first define B. let's take b equals 0. So for now, let's try with no trend, slope 0, okay? And then I can write y is equal to a plus b times time. Time is a vector varying from 1 to 20,000. So let's take it sec 1, 20,000. This is my straight line. Let's put it over the plot. Lines y. Let's do this. Sec 1, 20,000. Y. And line width equal 3. And let's put color equal red. Let's look at the plot. So this is the plot with my regression line. This is my model. The red one is my model. It's an horizontal line, actually, starting from 1486. Everything is clear. Now we have to estimate the sum of squares. So sum of squares, it's very simple. Sum of river flow minus y squared. I'm not really sure if I take the square in this way. I'm not really sure if it is squared the difference or the sum. So let me put a parenthesis. I want to make sure that what is squared is just the difference. This is the sum of squares. You see that it's a number that is difficult to evaluate. But still we can minimize it. We can find the value to minimize it, the value of the slope that minimizes it. But with a so large number, let's take a square root of it, because otherwise it's too large. When the number is so large, it's difficult also for me visually to evaluate it. Let's take the square root. Doesn't change anything. To find the minimum of the square root of the sum of square, it's equivalent to finding the minimum of the sum of squares. It's just a way of getting a visualization that is clearer. Okay, this is the result. Now let's try to change the slope and bring the slope to something like, let me try. I go back, instead of b equal to 0, b equal 0.01. And then I have to remake the computation. This is a trial and error procedure, okay? So let's get the y. It's recomputed, and then let's get the objective function. You see that it's decreased, so very good. 0.01 is better than 0. Let's try again. Now it's better if I clear the screen, but if I clear the screen, let me compute it so it's visible there. Okay, let's take b equal 0.02, y, and then sum of squares. It's increased, so it's too much. So the best value seems to be so far 0.01. But I should try with, I should make more trials, but it becomes a bit long. So in order to make more trials, let me write a function in R that computes directly the sum of squares depending on the value of b. So it could be, let me just check the symbols that I used here. It could be this one, sum SQ. Okay, sum SQ is a function of b. And then I need to open a curly bracket. No. Okay. And then I have just to repeat this computation y. And then sum of squares. But let me give name of a variable here, which can be result is equal to the sum of square, return result, and then my function is done. And now I can make sum of squares of 0. And I find the previous value that I already found. Sum of squares of 0.01. Sum of squares of 0.02. Good. So these are my results that I previously obtained, recomputed with the help of a function. You see that the function helps a lot in getting faster. And now what I can do, once again, if you get lost, I'm going fast because it's not the first time that we use R. And I want also to be efficient in helping you to gain in speed. But if you get lost, you have to tell me, okay? Otherwise, I keep going faster and faster. At a certain point, you have to stop me and say, you are going too fast, okay? I rely on your cooperation. So let me now do like this, a cycle, computing the objective function for 100 values, like for 100 is too much because they go out from the screen. So let's compute 10 values for I in 110. Okay, and I need to open a curly bracket. Let's make B equal, okay. Let's do this, C equal 0 plus I minus 1 times 0.003. Good. What I'm doing here is to compute the objective function 10 times, starting from 0 and incrementing the slope each time of 0.003. Okay, and now I can do the computation. Sum of squares C. And now let me print the value of C on the screen. So slope equal C. And then I go to a new line. And then I close the curly bracket. Let's see what happens if I didn't make mistakes. But I didn't plot. That's fine. I have to repeat it because I forgot to plot the result of the sum of squares. So let me just go back and let me clear the screen. Okay, clear the screen. Very good. Just 1 second. I go back for I equal 1 to 10, curly bracket. And now again, like this. Sum of squares. Let me just write here. List as equal. And then here, when I make the print on the screen, I have to make C and okay, now it should work. Here you see the results. So what is the minimum? We have the first one is, the second is lower than the first, the third is going down, the fourth is still going down, and it looks like at the value of 0.009, I got the minimum, and then it's increasing again. So the best value is 0.009. This is trial and error. trial and error, with the assumption that the intercept is not calibrated, is fixed. Okay, this is trial and error, and automatically I can do, how can I do that? As I said, any package has some guided searches. So let's try to use a guided search. And in R, you have several opportunities. The simpler one is optimize. Let me use the same, everything what I did is reported in this file. Let's take this function, this instruction, cut and paste. I put it here. So I am creating a variable which I call PR1, which contains the result of the function optimize. What I have to optimize? I have to optimize the function sum of squares that I previously created with the parameter slope varying in the interval from minus 0.5 to 0.5. This is how this optimization function works. I have to give it a function, which I previously wrote, which is computing the sum of squares. And then I have to specify the interval for the parameter. Now, let's see the results. This is the slope corresponding to the minimum, 0.08. And the objective function minimum is what you can see there. This is coherent with the trial and error procedure that I did before. It's coherent. The result is a bit different. Why? Because here the optimization is exploring more values. In the previous one, I just explored 10 values. Here I am exploring more values. But still, we fixed the intercept. So now you could say, how can we estimate both of them? I tell you the fastest option, which is a function in R which fits a straight line to any kind of data you may give. So let's write PR2 is equal to LS fit, which means least squares fit of what? We should give X and Y. So basically, it's the X is time, sec 120,000, and the Y is river flow. Done. Now, how can I see the results? PR2 coef, which means coefficients. And here you see the intercept and the slope. The slope is, it's, if you make 5.62 divided by 1,000. This is the slope, 0.0056, and the intercept is 1,515. Because the results are given in scientific notation. But if you want to see the result in numbers in order to compare with what I got up on the screen, you see that by fixing the intercept, I got a slope of 0.008. If I free the intercept, if I also estimate the intercept, the slope is 0.006, if you approximate. It is similar, but indeed, by freeing the intercept, you give more flexibility to the model. You are estimating the two parameters. Question, please. Yeah. In this case, this LS fit function can be used only for the estimating a linear straight line. And if you have a more complicated model, you have to use, for instance, optimize, like I did in the upper part, but you have to write the function sum SQ by also allowing the intercept to be estimated. So it is a step forward, and we will make it, but not today. Okay. We will make it because I will also I want to compute with you the estimation parameterization of the linear reservoir by using other data, and therefore we will make also this case. But for today, I just wanted to make clear with the simple example of the straight line. Yeah.
So
In this case, yes. In both of the cases, optimize and intercept, and LSFit, they are functions that are embedded into R in both of the cases. Optimize is more generic. LSFit, as I said, is only for straight lines, which is an important case because when you make trend analysis, as you know, because we discussed it, we try to estimate a trend line to represent the change and in a series of data. So it is very relevant. It's a very relevant example, but still it's a very simple model. And optimize requires that you write your own objective function for your model. So sum SQ is the objective function that we wrote. LSFit is automatic. He knows that it's a straight line, so it is computed independently by R. I hope it's clear. Yeah. Yes, LSFit makes free both of the parameters, but it assumes that the model is a straight line. If you want to use your own model, like we did for optimize, we should also allow the intercept to vary. But we didn't do that today because I wanted to make one step at a time. Okay, to conclude, I would like to tell you a story related to the trend. We talked about the trend estimation through a straight line, but what is a trend? And there was once upon time a relevant discussion among scientists. How can we define a trend? It's something that, I mean, cannot really be defined. What do we mean with a trend? When we talk about climate change, there is a trend, but it is a linear trend, it's a polynomial trend. If we estimate it through a straight line, is this really a trend? Is this really the trend that we mean? So they came out with a conclusion in this discussion, which is the lack of a definition for a trend. So one thing is a straight line representing a trend, but what is this trend? And the conclusion is that the best definition they could find, and you can find in the web reference to this story, is that everyone understands that what is a trend, but we don't have a mathematical definition for it. And therefore, they concluded that the best way to define a trend is a trend is a trend is a trend is a trend. So we understand what is, but there is no mathematical definition. We use a straight line for representing it, but why not using a polynomial? How can we define a trend? So I leave you with this nice story, which reflects also what is our understanding of these processes, how much limited is our understanding. So we decide to represent the trends through a straight line, but I could also represent it through a mathematical model. It's an interpretation, but actually what is trend? Is a trend or is a cycle? Who knows? Okay, sorry if I took a little bit more of your time because I was late, and I wish you a great Easter break. Take some relax, and we will see each other in 2 weeks from now, I think. Yes, so we have a long break, and so great, enjoy. And if you have any question, feel free to write emails. Maybe not on the Easter Sunday, but on the other days, even Easter Monday is fine. Okay, good. Ciao, thank you.